So in this capsule, we'll look at a new concept called resonance. It's one of the foundational concepts in organic chemistry. We use it almost every day. And we'll go to that concept starting with Lewis-dot structures of ozone. Before we go there, I have some data here which we'll use later on. I just wanted to introduce you. We'll use the bottom portion, but put the other numbers here too, because this is the bond length. The carbon-carbon bond length is measured in experimentally 153 picometers. C double bond C 134 picometers. C triple bond C 120 picometers. So what do you notice? As the number of bonds increases, the bond length decreases. Okay. Same thing is observed with oxygen bonds too. Oxygen single bond 147 picometers. Oxygen double bond 121 picometers. Okay. So let's keep, and we'll come to ozone after we come up with a structure for ozone. So again, there are 3 oxygen atoms. So supply is 18 electrons. Each oxygen atom brings 6 electrons. So 18 electrons supply. Demand is 24 electrons. The number of bonds will be 3. Okay. So since we have this information, I'll just put that there. Supply is 18 electrons. Demand is 24 electrons. And number of bonds is 3. Let's draw the structure. And since all 3 atoms are oxygen, so we can start with one oxygen, another oxygen, another oxygen. So we'll start with our making a single bond between oxygen atoms. So right now we have used step 4 electrons. There are 18 electrons total. So let's go about giving octet to each oxygen atom. Okay. You know, oxygen forms either 1 bond or 2 bonds. If it's neutral. Okay. So you can, let's say, put a double bond there. And so I have conferred an octet to this oxygen. So I'll show that octet in this fashion. So this oxygen, let's call it oxygen 1, has an octet now. But in doing so, we have used up 2, 2, 2, 6 more electrons. 6 more electrons are used up. So totally 10 electrons are used up. There's still 8 more electrons to be used. So let's go on the other oxygen atom. This one, and let's say we give that an octet. Now we used up another 6 electrons, so 2 electrons are remaining. The 2 electrons are on this oxygen. Okay. So you'll see each oxygen atom, this one has an octet. Let's call this oxygen 2. And then the central oxygen atom also has an octet. Let's call it the oxygen central atom. Okay. Now, so we we translate this boost dot into the more familiar oxygen, a double bond there, and a single bond there, and let's put the lone pairs on. Okay, so you got the structure. Now, we will still use those ones and twos on the oxygens. This is just to differentiate. It's the same, it's oxygen atom, right? Just differentiating between the left one and the right one and the central one. Okay. So you will notice in this structure, there's a double bond between oxygen 1 and the central oxygen, and a single bond between the central oxygen and oxygen 2. So you expect, based on the structure, two different bond lengths. So the oxygen-oxygen single bond will be like 147, and oxygen-oxygen double bond will be like 121. Right? But, okay, skip that. It's there. Now, you may come up with an alternate structure. You may notice I use the double bond between the oxygen 1 and oxygen 2. Or you may come up and say, hey, I want to do this one. So, now, do it this way. So, and this one, oxygen 1, oxygen central, oxygen 2. Now the single bond and double bond change locations. So, still ozone, and now this double bond, single bond can either be on the left side or right side, like these two structures. So both structures are possible, both structures happen. The true structure of ozone is something in between. Now, how do we prove that? Experimentally, so people made measurements, and we know the hydrogen, like this one is from like H2O2, hydrogen peroxide. The oxygen single bond length is 147 picometers, and oxygen double bond, like in oxygen itself, the molecule 141 picometers. So if ozone is either this or that, it should have two different bond lengths. But experimentally determined bond length in ozone is 128 picometers. So it cannot be either this or this. So it must be a hybrid, which means there's the two bonds there, oxygen, oxygen, oxygen. So the double bond and the single bond are not fixed, but in a constant motion, in a flux. So to show that, people start using a notation like this. The double bond is like that. This is what is called resonance. When double bonds and single bonds change location, it's called, that phenomenon is called resonance. Okay. Now, we'll do many examples. We'll take a look at different examples of resonance so we get some practice on this. Okay. Now, one more thing before we stop this capsule. So let's do ozone. If you look at this, it doesn't look like there's any charge on the oxygen atom, but you already know, we have talked about this. Neutral oxygen will have two bonds, and an oxygen that has three bonds will have a positive charge. So notice this oxygen here, the central oxygen atom, has three bonds, so it will have a positive charge. And the oxygen with a single bond will have a negative charge. So that's, you put the charges on them. Likewise, if you take this resonance structure of ozone, the central atom still has a positive charge, and the right oxygen has a negative charge. So, but overall the molecule is neutral. Now, in this resonance structure, now that you have found this resonance, which is the true structure of ozone is something in between these two, which is experimentally borne by the bond length. So both bond lengths are identical. That means it has to be moving, the double bond needs to be moving back and forth between those two oxygen atoms, as a result of which the negative charge also moves around. So we say there's a half a negative charge there and half a negative charge there over. And this structure is called the resonance hybrid. So neither this structure, not this structure, but the true structure of ozone is this, the resonance hybrid. This is the experimental proof. The bond length is in between the single bond and the double bond. Okay. To explain that, this resonance concept came about, and it's a very crucial concept. It's seen in thousands of organic compounds. It explains why one compound forms in a reaction, not something else, or one compound forms more than something else, another compound, another product. So let's do some examples of this concept, resonance. We'll take a look at bicarbonate ion in another video, and maybe we can even take a look at ATP, because it's a biological molecule, and we'll just draw that and see how that ATP has resonance, some parts of ATP. Okay. Now let me erase this, and we'll show one more thing, and then we'll stop this short video. So how do we denote? So okay, we drew the two contributing resonance structures. So we had this structure, negative charge plus a neutral oxygen, and the two resonance structures are shown by this arrow. This double-sided arrow like this, that indicates the left structure and the right structure are resonance structures. Okay. Now, the other structure we had was like this, plus O minus, right? So notice in this one, in this structure, I omitted the lone pairs. We do not need to show the lone pairs all the time. So if we show the lone pair, it's like this. The lone pair here. That way. Okay. But going forward, we need to remember stuff. Some of them, like neutral nitrogen has one lone pair, neutral oxygen has two lone pairs in molecules. A neutral oxygen atom will have two lone pairs, like this one here. Okay, positively charged oxygen atom has only one lone. So these things should become part and parcel of something like we need to remember those things, so we don't need to do all this analysis all the time. Okay, so anyway, how do we denote this resonance? So how do we show it? That is what is called the process, the pictorial way of showing that, how this particular structure became this. So you can see this electrons, two electrons that moved, right? So that is what we show it like this. So these two electrons moved here to form a double bond, and then these two electrons, one of the two bonds, the single bond is a sigma bond, the second bond is a pi bond. So the pi bond electrons move to the other oxygen. So now, if you show that, one lone pair move to form the double bond. So this oxygen atom has two lone pairs. The central oxygen atom got the electrons and it give them away to the next oxygen, so no change there. But the third, this oxygen atom, this double bond electrons move to the oxygen atom, so what it has two lone pairs originally, now it got the third one, so that stops there. So this notation is again a very important one. We need to master this as well. Curved arrow. Okay. Curved arrow. You start with the electrons, move them, and then you move the double bond there to the next oxygen atom. So we need to master these two things, resonance and curved arrows. We'll do that in the next capsule. We stop now.